Okay, guys, let's start with topic 24 right now, and let's proceed that way. I am going to refer you to the back of the chapter where they show some of the formulas. So you look at those, and then that'll kind of make sense. What I'm going to be doing is going to make a little more sense to you in that regard. So let's in the interest of saving a little bit of time, you're looking at pages 807 and 808. 807 and 808, they'll tell you a lot of the stuff. I'll write some stuff as well, obviously, when I'm doing this, but something to kind of look at in this regard. Again, read as much of this as you can, you guys. Obviously, I sound like a broken record here. This is less than ideal. Let's talk about interference patterns that happen with electromagnetic waves. Let's talk about problem number 7. Problem number 7, they say 2 radio antennas separated by a distance of 3.0 times 10 to the second meters, as shown in figure 24.7, simultaneously broadcast identical signals at the same wavelength. A car traveling due north along a straight line at position x equals 1.0 times 10 to the 3 meters from the center point between the antennas and its radio receives the signals. A, if the car is at the position of the second maximum, after that at point 0, when it has traveled distance y equals 400 meters northward, what is the wavelength of the signals? B, how much farther must the car travel from this position to encounter the next minimum in reception? Hint, do not use the small angle approximation in this problem. Okay, this is a great problem. Try to do something. You got the picture. They drew a much better picture than I'm going to draw, but they're talking about here's the car. This is the y-axis, this is the x-axis. These are the 2 radio antennas broadcasting outward. They're going to make it to the car. The radio's somewhere here, you know. The radio receiver somewhere there. And let's see what they're talking about here. They're talking about the second maximum. They're talking about the minimum. It is a very interesting problem. Let's take a look at it. We remember a number of things, and I'm going to write down those number of things actually. This is true, period, simple as that. And in the big picture here, we can kind of look at this and say, okay, this can kind of be mimicked looking something like this. And you could have, there's something here, it's kind of like that diffraction, Young's diffraction experiment that we were talking about. And this guy fires this way, guy fires that way. Right down the middle is this guy. That's theta. That becomes a hypotenuse. That becomes a leg. If you do all the trigonometric identities that are to be talked about here, you got to remember now, this thing right here, this is also theta. And if the whole thing is 90, this is 90 minus theta. This right here is also theta. Pretty important stuff. This is D. And the way I wrote it, I mean, this is actually better than the way my notes look on that. So this guy right here, the way I kind of wrote it is it wasn't clear when I first, this is more clear, you can see it a little better. When it wasn't first clear, I say that's theta, you know, that thing I'm pointing to right there. This distance right here, call it delta, lowercase delta. Is d sine theta. For constructive, we'll go a whole 9 yards on this one, guys. I think we got the whole thing set if we do this. For constructive interference, when you got delta, the path difference is d sine some kind of theta. The theta changes. I didn't really kind of write that in the notes, but I kind of should. Depends on the theta that you're talking about. I mean, depending on the angle, there's a different theta. I didn't really show that here. The book shows it. In the notes, I didn't put that subscript. I should have. You can argue it a whole bunch of ways, I guess you want. You can put it there, you can not put it there. It's not a real big deal. The theta is going to change. Whether you have theta sub m or not, I don't know that it's the biggest deal in the world. But this is true when the path difference is an integral number of wavelengths. There's no path difference at all, that's 0. There's a path difference of 1 lambda, of 2 lambda, of et cetera, et cetera. The theta, like I said, the theta sub m, it's not, I mean, you're probably gonna, guys where you hear me make those jokes with you guys, you're probably gonna want to punch me in the face at the end of all this, you know. I know the guy filming me wants to kill me right now, but I understand. But we got, you know, either way, it doesn't really matter. The theta's the theta changes, okay? So we got this. Now keep it in mind. I mean, the theta is variable. You know, put theta sub m. That's probably the most rigorous way to do it. If you don't, just know that theta changes. If you change theta, you are going to be changing the path difference. The path difference becomes different, and there's a different path difference associated with it. And you got this. This is for constructive interference. This is some pretty big time stuff, you guys. Pretty fascinating stuff. How that all works out. See what else we can say. That's for constructive. For destructive interference, so for destructive interference, you guys, now and I'll talk to you about it, but let's sort of put the carriage in front of the horse on this one, you guys, a little bit. For destructive interference, you're talking about the path difference being this. Absolutely, and that would happen again. You know, the path difference would be this, and that would occur at some other angle. You know, some other angle theta, and we're talking about m being equal to. I'm not crazy about how I did this in my notes, to be honest with you, but this tells you something as well. All right, what's going on here? Well, I mean, I've been kind of thinking about that from day one, so I don't get to see you guys for about a month or two at least. So we'll see how this all works out. But here's what's going on, you guys. There is, for lack of a better way to say it, there is a point right here and a point right here where this is a source of electromagnetic waves. And this is also a source of electromagnetic waves. And let's say they're simultaneously broadcasting when this is happening. They're simultaneously sending out the signal. Nobody's delayed vis-a-vis anybody else. They're simultaneously doing this. Somewhere, and this is kind of more of an approximation than anything. These actually, if you look at the book, the notes in the book, these actually are converging to one place somewhere. Maybe, you know, it could be. Try to try not to beat this thing to death, you guys. It's going here to the radio receiver, so to speak. There's a path right here, and there's a path right there. And this is a distance D1, and this is a distance D2. The difference between the two is delta. Delta is D1 minus D2, and that's given by that length right here. If it's far enough away, this is very awkward, guys, but let me tell you. If the radio receiver, for example, is far enough away, these two lines behave as though they're parallel lines. They behave like this. Let's say this is just a real close-up of them. Further down the road, these two lines do bend into each other. They were bending into each other from the very beginning. But the distances are so great, oftentimes, relatively speaking, the distances are so great, the triangle that these guys belong to, where they merge to a point, they resemble parallel lines. And that's kind of what's going on here. They resemble, they don't look like it here, but if it's a real big enough triangle, real far out there, at some level they sort of, kind of approximate parallel lines. This distance right here is the delta that we're talking about. And that delta is, like I said, some multiple of lambda. If it's constructive interference, they gotta differ by an integral multiple of the wavelength. If they differ by half a wavelength, or a multiple of half, or a multiple of half wavelengths that is odd, namely this right here, the waves will hit each other in a way that they destructively interfere with one another, and the receiver won't really pick up the waves. Here the receiver will pick up the waves for constructive interference. For destructive interference, so that's constructive. And then, like I said, it's all this business here. D, ML, M lambda rather. D is this guy right here, that distance. D sine period. Down the road, they could destructively, if they destructively interfere, it's looking like this. And that's kind of what I was talking about there. So, not a great way to say it, guys. This is where I need you. This is where I need people right in front of me, I guess, with whom I can speak, people with whom I can speak, so we can all speak together. We can't do it, so we're doing it like this if we can. But that's kind of what's going on. This right here is a real big, this is the big picture. This might be 90 miles away. This might be, 150 kilometers away from this guy. There could be a 150 kilometer distance. If that's the case, they look like this up close, like parallel lines. And that's some of what's going on when you're trying to play the game with constructive interference and destructive interference. Had to be talked about a little bit, so we're doing that. If that's the case, you guys, they want to find the second maximum. How are you gonna determine it and go for it? So let me see how we're going to say this. I'm probably going to have to go to multiple boards on this one. So what we said for this, and for problem number 7, okay, so we got for this one, m equals 2 second maximum. Here goes. Okay, we saw some, at least we did some of the mathematics there. We got that. M times lambda is what delta, this delta delta and m times lambda are the same thing. So they're the same thing. We got that. We got 2 lambda equals d sine theta. Not bad. That's a big move. This is going to get us there. This is going to get us there. If that's the case, we'll use some of the data that they showed us, you guys, and we'll kind of take it from there if we can. Let's see what we got here. We got, okay, so we say for A, we're going to say 2 lambda equals d sine theta, divide by 2 on each side. Lambda equals d sine theta over 2. D equals, well, they're telling us that they're 300, the D is, they told us they're 300 meters apart. That the towers are 300 meters apart. The broadcast stations are 300 meters apart. 2 is 2. 300 divided by 2. What's the sine of theta? Sine of theta is y divided by the hypotenuse. Basically, they gave us some stuff here, guys. We went over here. We talked about, take it right about here, I guess you could say. That's x. That's y. This is the square root of x squared plus y squared. Here's x. Here's y. Here's theta. The sine of theta is going to be y over the square root of the quantity. Y over the square root of the quantity, x squared plus y squared. What do we got? Well, we got this. $400 is the y. We were told when the car was located at 400 at that moment. And 1,000 was the x, and 400 again was the y. 400 was the y, 1,000 was the x, and the rest is math. The rest is math. Lambda, the signal for this to be the case, what they told us, would have to be that. Notice, I didn't have to find, I can find out what theta is. I just get the inverse sine of this ratio, of this particular ratio. The inverse sine, we can find out what theta was. Nobody, I mean, at this point, nobody asked. I'm going to look further on, see what they're asking, but this is what lambda is going to be. That's pretty important stuff. And in fact, what am I talking about? They are going to ask what the angle is, so we're okay. I mean, or no, let me hold off on that. Now they're saying here, where would, you know, at what angle, so we could find that theta, whatever it's going to be, it's going to be. They didn't ask us to find that one, but they are going to ask us for another theta. For 7b, they're saying find the place where the second destructive pattern occurs. Where m equals 2 for destruction, for the destructive pattern, what would that be? Well, okay, I already know what lambda is. I know all these equations that are up there. So we're feeling pretty good about that. So let's see what we have. M equals 2. If it's going to be a destructive situation, it's m plus a half times lambda is going to get us there. Delta equals d sine theta. All right, well, the deltas are equal, and we said that. I mean, how that's all going to work out. Let's do the song and dance that we know how to do. goes. They are asking us find the angle where that's going to happen, and then we're going to, find the angle and find the location. Pretty interesting stuff. Pretty fascinating stuff, if you ask me. Let's do some stuff here. Let's find. See, they want us to find the location, the Y location that it's going to be at, and I'm thinking. There's a whole bunch, there's a number of ways to go here, and perhaps this isn't even the most efficient. We could have just left, well, no, we got to do it. There's going to be another location, guys. There's going to be another, I did this now for the constructive interference pattern. It is much of the same mathematics when you do it for the destructive interference pattern. For the destructive interference pattern, it's going to be much of the same pattern. Same mathematics in a sense. Okay, so here it is. Let me find out how far out Y it's got to be for there to be destructive interference. Well, to do that, the trigonometry is essentially the same. Let's be patient. Let's see what we can do. So we've got this. Do some math. Divide by d on each side. Forgive me. Yeah, right, exactly. Divide by d on each side. You got this. Let's figure out some stuff here, guys. The sine of theta is going to equal, we want m equals 2. M equals 2, so m equals 2 plus a half is 2.5. Times lambda. We already discovered lambda. Lambda ain't going to change no matter how you fire this thing off, what direction you're putting these signals. D is 300. D is the distance between the two towers. And that's 300, that doesn't change. Yeah, it's this right here, guys. So here's here, and that's D. D's equal to 300 in this case. So for that whole process, right, for this whole thing right here. Now they're not connected in any way, I'm just putting the line between them to show you that's D. They're not connected beyond that. They said don't use the small angle approximation. The ratio's too big, you guys. The ratio's way too big. Don't go there. Don't go there on this one. You got this. Get the inverse sine of each side. Okay. They didn't ask me that as a final answer, but they're asking me something else as a final answer. What is the distance? I mean, how much further would it go? I think the way they're asking on this one is, how much distance would it have to travel? Here it's at 400. I think they had it. Yeah, right. This was the x. The x was 1,000 meters. The y was 400 meters. How much further would it have to go for that destructive interference pattern to happen? Well, I'll tell you what. Let me call that whole distance the 400 plus the further, the 400 here plus the further up here, all together, let me call that y prime. Let me say this. Let me say that y prime, that's the total distance from the base. This is y up here, that would be y prime. The extra distance right here. We'll just call this d. D the distance to go up there. So d plus y is going to be the y prime. Going all the way up to there. Well, that's going to be a new angle. I mean, this thing's going to, that's obviously a new angle. It's a different theta. The trigonometry doesn't change, ladies and gentlemen. The trigonometric realities, doing the trigonometry doesn't change. Y prime over x equals the tangent of 27.661 degrees. Simple as that, you guys. It's going to be, we already know that new angle is something different. That's, you know, what that angle was over there. Not as big an angle. I can practically guarantee that one. But this angle's big. The angle that we got, so just be real careful here. Right, that's about right. That's the angle we got. So from there, y prime is equal to x times the tangent we said it was 1,000. $524.14. Yeah, that's the whole thing. How much further did it go? Well, we said that y prime equals d, the further, plus y is equal to 524.14 meters. Yeah, well, d plus 400 124.14 meters. Yeah, that's it. That's it. So let's go to 13. We okay? I mean, this okay. All right. So it's all on there. It's a lot here. It's beautiful stuff, guys. If there is any one good thing about how we've done this class is we've made everything open book, open notes. I mean, it kind of lends itself to doing some great problems, and you're not caught in some situation where you're trying to figure something out and not be able to look at notes. I mean, this stuff is complicated enough. I mean, there's nothing wrong with, I think, being allowed to look at the notes on this thing. So we are where we are, guys. Let's make this thing work. All right, if that's it, that was number 7. Let's go to number 13 for this same topic, 24, and let's see where it goes. It's a topic 13. You got to watch your step, but we can do it. We are continuing. We're going to look at number 13 from topic 24. It is a bit of a messy problem. It's a great problem, nothing wrong with that, but let's see how we're going to play it out, and I'll tell you some of the assumptions that we got to make. The drawings I made are not the greatest. My notes have the drawings done probably better than what I did on the board, but let's take a look at it and see where we are. So we're looking pretty good. Let me read something to you. For problem number 13, topic 24, radio waves from a star of wavelength 250 meters reach a radio telescope by 2 separate paths, as shown in the figure. One is a direct path to the receiver, which is situated at the edge of a cliff by the ocean. The second is by reflection off the water. The first minimum of destructive interference occurs when the star is theta 25 degrees, theta equals 25 degrees above the horizon. Find the height of the cliff. Assume no phase change on reflection. We are going to assume that there's no phase change on reflection, you guys. So the way in which the wave is oriented after it reflects is the same as though it took a direct path to get there. They're saying a bunch of stuff here. Let's make it make a little bit of sense. What we have is you've got a path like this, coming straight. Here's the cliff. Okay, here's the assumption we gotta make. This whole thing, this box right here that I drew, is the cliff. This box that I drew is the cliff, and the radio telescope is on the cliff. And this blue dot I put here is the radio telescope receiving all the signals on the cliff. So the cliff and the radio telescope are one entity. We'll call it the cliff. We're saying it's just, we're not going to concern ourselves with how tall the radio telescope is. We're going to say the radio telescope is just right on the cliff. Make that assumption. Here's your radio telescope. Here's the height of the cliff, h. Radio waves are coming in from the star from far away, this way, directly, and they're also coming in this way. Bam, they're hitting right here, and then they are reflecting to come over here. And these thetas are the same. They don't look the same. I didn't draw it too good, but we're going to say, you know how reflection works, you guys. If you hit at an angle theta, it reflects at an angle theta. If this is angle theta, if this right here is angle theta, you guys, this right here is also angle theta because of the nature of the law of reflection. The two angles are going to be the same. So you've got a path here, and you've got a path here. What's going on here? Well, what's going on is, what's the path difference? And here's where you got to be extremely careful. We got to find the path difference. We got to look at a few things. They're saying there is, in this particular arrangement, in this particular configuration, they're telling us the first minimum of destructive interference occurs there. So it's a minimum of destructive interference. We got to look. We got to talk. There's a lot here. I mean, there really is big time a lot here. This guy, you know, what's the difference here? The difference in the path, you guys, is, you could say a whole bunch of things, I guess you could say on that one. If you drew this right here, and right here, and you drew this there is a difference of this much. This D1 is D1 more than this right here, right when it hits the water. Yeah, but not so fast. This guy also has this far distance to travel. We'll call that D2. So this guy's got him beat by D1 from right here. If you're just taking a look at right here, if you're just taking a look at right here, this guy is going further. Just looking right here, this path is D1 longer. So from here to here, all this and all this, they're equal. Then this much more path to get to here. D1 more than this. Here, this is X and that's X. Add D1, it went that further. Yeah, no, but this goes further, D2. So at the end of the day, the delta is, yeah, one of them's got them beat by that much. One's like, I guess you could kind of say, the way they all play out is, the long guy is X plus, let's just call this, from here to here is D. From here to here, I'm sorry, forgive me. From here, you know, or from wherever. From way out there to here is X. From also way out there to here is also X. Parallel lines, or close to parallel lines at least in the approximation, and they both travel the distance X. Very long distance X plus D2 is what the bounce one did. Traveled the distance X from way out there. It could be a quasar for all we know in a very far away galaxy, and that distance is X. Here's X, here's X. Here's D1, here's D2, right here. Yeah, they're both x. The long guy is this guy. It's going to be x plus D2. The short guy is this guy, x plus D1, because he also has a little bit more to go. When you do the subtraction, x plus D1 minus x minus D1, x minus x is 0. So we got this. We are told, that's important, we are told that lambda is 250 meters. We are told that theta is 25 degrees. We are told, well, we can conclude about delta that this is D2 right here, guys. How are you going to find D1? D1 is D2 sine alpha. Let's put an angle here, alpha. So let's see here. D1 is equal to D2, the hypotenuse. This is D2. That's D2. D2 times the sine of alpha will give you D1. So, get more. Times the sine of alpha, D2 yeah, that's absolutely that. If that's the case, I mean, there's a lot you can do. You tell me what's the better way to go here. I mean, it's sometimes a horse apiece. Take D2 out of there. So there's a lot to look at. They both mean the same thing. A couple ways you can look at it if you want to look at it. Well, delta equals delta, guys, and we said the path difference is the path difference. So we also know that it's the first destructive interference is going to happen. The first one, that means m equals 0. So when m equals 0 and it's going to be destructive interference, delta is going to equal m plus a half times lambda. Put a 0 right here, that's 1/2 lambda. So that's delta, right here, that's delta, and that's also delta. So, I'm not going to say anything too profound here, guys. Delta equals delta. 1/2 lambda equals D2 times 1/2 sine alpha. Okay, let's keep talking. We know that's true. We can also say that there is a height and there is a hypotenuse D2 and there's a height. How about h over D2 is the sine of theta? Maybe that'll help us talk a little bit about what we're doing. So h over D2 is the sine of theta. Which implies, I mean, let's solve for D2. Let's multiply by D2 on each side and divide by the sine of theta. Multiply by D2 on each side. D2 equals h over sine theta. So, okay. Let's see what else we might want to say here. Might as well bring alpha into the game. The sine of alpha is opposite over hypotenuse. D2 shows up again. D1 over D2 is the sine of alpha. These are all in my notes. Okay, we got a lot going on here, I guess you could say here. It's pretty interesting how this is all working out. So you got this. Let's come back. Christiane, I don't think that shows up good, but it shows up okay, right?
It's okay.
Okay, it's good enough at least to show that I've emphasized something. Okay. I'll kind of do it just for those purposes. I won't do too much beyond that. So you got 1/2 lambda equals all of this. And, you know, there's some stuff we can talk about. I mean, we said, let's basically say a couple things here. We got this, and then I want you to observe something, guys. They want us to observe, they meaning me, I guess. I want you guys to observe something. See exactly how we want to maybe look at this thing. Are you guys okay with the fact that this is a 180-degree angle? This thing right here, this thing called the ocean. There's the ocean. That's a 180-degree angle. What is that? Theta plus 90 plus alpha plus theta. Sounds good to me. Theta plus 90 plus theta plus alpha. What's going on here? Plus alpha plus theta, rather. Doesn't matter, right? So theta and theta is 2 theta plus 90 plus alpha. Basically, let's just read it. Theta plus alpha plus 90 is the whole 180. We can see that from observation regarding the figure. I mean, there's stuff I can do. I don't know if I need to go there, but all of that is true. I subtracted 90 on each side, got it down to here. You know, depends where you want to go. When do you want to get off this merry-go-round, guys, when you're doing the thing. But you got this. So let's see what else I actually did here. When we did this, I'm trying to not have as much in the process here as what we had. The big move is here. I mean, it's at least one of the big. I mean, there's a lot of big stuff here, but we've got this. We're not forgetting this, and we're not forgetting this. So those two are pretty big. We've got to not forget them. You got delta right here. You got delta. We're looking pretty good. So I mean, it's essentially. Let me keep going. We wrote it. We got to here. This is pretty big. Wait, you know, let's time out for a second. You get down to here, man. They already told you a lot of stuff. Alpha is going to be 90 minus 2 theta. Didn't they say it was a 25-degree angle? They told us it was a 25-degree angle. So I think it's pretty important. Very important, obviously. You know, 2 times 25 is 50. 2 times 25 is 50. 90 minus 50 is 40 degrees. So, yeah, sounds good to me. Let's look over there. Okay, we look way over to my left-hand side, your left-hand side, I guess, too. If you were standing behind me, we both look at our left-hand side. We got this. We got delta equals 1/2 lambda. We have delta equals d2 minus sine alpha. Well, I'm not really saying anything too profound here when I say that delta equals delta 1/2 lambda got this. I guess you can, there's a load of ways to play this thing, I guess. Let's take a look at it. I mean, you got this. Let's solve for D2. That's a pretty big thing. Once I got D2, I'm done. I'm just about done, guys. Once you got D2, you've got the hypotenuse of this right triangle. To find H over D2 is going to be the sine of theta. They already know what the sine of theta is. It's 25 degrees. So I think we're good. I think we're looking real good. I mean, you go right here. A lot of that was happening from over here. All the moves we made to get to here, they're coming on over here. So let's deal with it. They told us that I think did we find it or something? I think they already told us anyway. They're saying the wavelength is 250, so the radiation of the stars are 250 meters. So yeah, that sounds good to me. So let's see what we got here. Go right here. Go 1/2 of 250 meters. Half of that equals D2 over 1 minus the sine of alpha. Now again, this is now just about old news. So you can, you go about it the way you want to do it, but D2 is going to be this divided by this is 125, and then divided by 1 minus close to 350. Yeah, there's the reflection. That's the hypotenuse of the whole thing. The rest should be pretty smooth. The sine of theta. Remember what's going on here. D2 is looking like this. The height of the cliff is here. The D2 is here. Theta is here. That's 90 degrees. So sine of theta is H over D2. Sine of theta is H over D2. And what does that mean? Well, it means a lot. I mean, it means H is D2 sine of theta. That means H is, we just said what the D2 was, got to here. It's not a real bad problem, but it is a great problem. I mean, I'm not talk too much until I get it done, I guess, right? sine 25 degrees. It's a great problem. It forces you to appreciate trigonometry, if nothing else. I mean, it makes you appreciate the trig class you took long ago, right? I mean, it's so it's good stuff. Good stuff. 147.89 meters in height. Some really beautiful logic that goes into the solving of it. It's very good stuff. Very good stuff, guys. That is 13 from topic 24. Let's go to problem 59, also from topic 24. So it should be somewhat easier to do, a little less convoluted. Again, you're looking at, guys, I really hate to be throwing you to the book the whole time on this thing, but we're going to have to, given our circumstances. Make sure you're looking at the book. Make sure you're looking at some of the equations that they're given to us. And what we're trying to say regarding that, so we'll kind of take it from there. So this is good. I mean, this is all right for us, guys. Let me go to problem number 59. Let me erase this, and we will do it. All right, guys. Let's look at 59. For 59, you guys, there's some formulas how things proceed here. So let me just kind of get to it. For problem number 59, three polarizing plates whose plane, you can see that in the book. Three polarizing plates whose planes are parallel are centered on a common axis. Excuse me. So three polarizing plates whose planes are parallel are centered on a common axis. The directions of the transmission axes relative to the common vertical direction are shown. A linearly polarized beam of light with plane of polarization parallel to the vertical reference direction is directed from the left onto the first disk with intensity I sub I equals 10 units, arbitrary. It's an arbitrary thing. Calculate the transmitted intensity IF when theta 1 is 20 degrees, theta 2 is 40 degrees, and theta 3 is 60 degrees. So it's a bit confusing how they drew this, but we'll figure it out. Make repeated use of Mollison's law. So what's going on here, you guys, is for this particular problem, I'm trying to figure out exactly what they've done. They've drawn this in a way that's maybe a little bit confusing. But anyway, there's going to be transmission that's going to take place, you guys. And the general law is the intensity, depending how the axis is hit, if it's not hit straight on, there's going to be something lost in intensity. Intensity is I0 on cosine squared theta. Yeah, that's for one item. If you look at this, they're making it so how are they in reference to one another? So let's see here. Three polarizing plates whose planes are parallel are centered on a common axis. The directions of the transmitted axis relative to the common vertical direction are shown in the figure. So everybody's off a little bit. Let's see how they drew this. Actually, let me try to draw something here. Something like that. This is straight up and down. and everybody's off center a bit, so to speak. This is theta 1. This is theta 2. And this is, I mean, they've drawn this in somewhat of a different way here, guys. I'm doing a little different. If you look at the book, I think the book is still better than mine, obviously, but look at something like that. This is where this guy is right here. So, I mean, they do dashed lines here. I don't think that means a whole lot, but let me kind of do what they're doing. So everybody's off center a bit, and you know, there's something coming in. There's something going to come out. It's going to be IF coming out, and you got II coming in. They want you to know the IF. So, a lot of ways to go. Repeated application of Mollison's law will actually get you. So, what happens is you got to look at the angles relative to one another. This guy's at theta 1. This guy's at theta 2, but in reference to him, he's theta 2 minus theta 1. This guy's at theta 3. These are all in reference to the vertical. In reference to the vertical, yeah, this opening here is theta 1. In reference to the same vertical, it's theta 2. In reference to the same vertical, it's theta 3, depending where you are. Here's theta 1 in reference to the vertical right here. Right here, theta 2 in reference to the vertical. Right here, theta 3 in reference to the vertical. Yeah, I know. This is what you started with. Then it goes here. The difference between the two, because it's already been knocked off center. So then go with the new center. This becomes kind of the new center. You go theta 2 minus theta 1. Here it's been knocked off center further to this guy. What's the new center? So this, and this kind of run the show when you're doing applications, repeated application of Mollison's law. So what you're going to do is, this is Mollison's law, and you're just going to repeatedly apply it. The answer, this new I is this. Once you got that, this is the new initial, and then you put other ones onto it. I showed it in more detail in the notes. So that's there for you guys. Please look at it. Kind of cut to the chase on it, I guess you could say. The way it goes is, again, look at the notes. I want a little more detail on it. But right now, let me just do this. IF at the end is the I initial guy, and he hits like this. Well, that's what I said the law was to begin with. There's going to be less transmission if you don't hit it. If the axis of transmission is not lined up perfectly, so you have 0 degrees between them. The cosine of 0 is 1. I0 will be IF. II will be IF. If they're lined up perfectly. They're not. This is what happens. This guy right here becomes the new II. And you're going to multiply it by cosine, the angle between the two. Then, this guy becomes the new I. And you're going to multiply that with cosine squared, theta 3, theta 2. Get more chalk, you guys. I kind of can actually used pretty well. The ivory chalk's not bad either, right? The yellow, the ivory's pretty good, okay. That's it. All of these. I mean, you're going to hit all of them. I mean, you're going to, at the end of the day, it becomes IF equals II times cosine squared All right, it's the same thing I wrote up there, you guys. It's the same thing that I wrote up there. They told us it's 10 units. Who cares? We told you the units mean nothing, you guys. As long as you're consistent with the units, you're okay. It's an arbitrary thing to say it's 10 units associated with what they want to do. And then they go theta 1 is 20, theta 2 is 40, theta 3 is 60. Okay. Theta 1 is 20 degrees. Theta 2 is 40 degrees, so 40 minus 20. Kind of interesting how that worked out. This is 60, that's 40, and 60 minus 40 is 20. Wonder how that all played out. And there it is. So basically the whole thing, you got cosine squared 20 degrees occurring in 3 places. Cosine squared 20 degrees, here's 10. Cosine squared 20 degrees occurring 3 places. All right, I mean the rest is formalities, guys, and even to the 6th power, I mean it's quite a bit. Uh, 6.89. Yeah, 6.89 units. After all that, a lot came out. A lot came out of that. A lot of it didn't get filtered out of there. You know, so it came out. A lot of the intensity didn't get stopped. And there you go. There you go. That is that one. Let's go to topic 25, you guys.